Oh, we're back. Oh, look at that. Some more studying. Okay, let's see. I think one of the things I need to do. I think this is okay, but let's find out.
So we do have
We're good.
3 hours
Nice.
together.
Oh God, that's not what I wanted to hear. 3 hours?
Autonomic nervous system.
3 hours?
I know that you've talked about
Oh
the
my
autonomic
God.
nervous system
Holy
in
crap.
physio. We're going to be talking about it from just a strict anatomical standpoint. And then we will move on to pain and temperature. And then we'll come back to the autonomic nervous system.
Here we go again.
Talk about cranial nerves. So I think sort of toward the end of next week, we'll be moving on to cranial nerves. And what we're going to see today is that in the brainstem, there are nuclei that give rise to neurons of, in particular, the parasympathetic nervous system. So when we talk about the parasympathetic nervous system associated with many of the cranial nerves, we'll come back to this. So we will talk about cranial nerves, as I mentioned, and the autonomic nervous system in AS1 and next semester in AS2. Okay. So with that, just a bit of just general background about the autonomic nervous system. So it's what we think of the functions that are automatic. So that's how it got its name, the autonomic nervous system, automatic. So it's things like breathing and cardiovascular control, heart rate, right, blood pressure, temperature regulation are all associated with the autonomic nervous system, and it's critical for survival. And I just put a little note here about familial dysautonomia. So life expectancy has increased with treatment, but the symptoms are treated, right? So it's symptom management. And again, without control over the autonomic nervous system, that's life-threatening. So in thinking about maintaining body temperature, blood pressure. And this is also associated with individuals with high spinal cord injury. So individuals with high spinal cord injury, they're not able to control their autonomic nervous system the way that we can. So like temperature control, blood pressure, right? All of a sudden it can skyrocket or drop very low. So it's very dangerous. And I just put a little note here about familial dysautonomia. So it's been identified, and it's noted that where some of the pathology is, it's a autosomal recessive disorder, and there are variations within individuals, but you can see a couple of locations, right? So the lateral horn of the spinal cord, that's a region that we're going to be talking about. The superior cervical ganglion, we'll talk about that, as well as some specific locations of the targets, like innervation to blood vessels, for example. So it's specifically associated with the neurons, the specific pathway to the target. Do you guys have a question over there?
Yeah, when do we get to go?
Oh, okay. So it was your no, that was your fault. Okay, I'm just kidding. Yeah. Okay, yeah. Just let me know. It's funny. There are all these. You probably know there are microphones in the ceiling so that we can hear. So like all I can hear is. So if you have a question, yeah, just let me know. Okay. Okay. So at any rate, that's familial dysautonomia, and again, it's impaired control of the autonomic nervous system. And this is just a general scheme of the autonomic nervous system. And as I mentioned, this is what we're talking about today. We're talking about the specific neurons within the central nervous system and specific neurons in the periphery that head to a target. So even when you think about, so just to go over this just very generally, again, I'm not going to ask you any specific questions, which is what this says. Really, we're focusing on what's in the red box. But when you think about, we'll talk about the amygdala, for example. So the amygdala is this is posted. I posted it later. Yeah, so it is. I put a little note there. If you downloaded this yesterday, this slide wasn't in there. I actually was sort of thinking about some of the sort of the inputs that ultimately drive the autonomic nervous system. So at any rate, when you think about, like the amygdala, we'll talk about it later on in the course. Again, I don't want you memorizing it now, but it's really important in like emotional centers. And I think about if you were to, sometimes like if you're giving a presentation, maybe you're nervous, right? What do you feel? You feel your heart rate going up. Maybe you feel like your face is flush. So we actually have like cortical regions and regions associated with the limbic system that can communicate with the hypothalamus, and then the hypothalamus is what drives the autonomic nervous system. So that like change in heart rate and maybe that flush feeling of your face, that's associated with the autonomic nervous system. There's also sensory information. We can produce saliva, as you know, if we put food in our mouth. But I just have to think about Sour Patch Kids. I mean, think about Sour Patch Kids. I almost feel like my parotid gland producing secretions. You almost sort of feel like those myoepithelial cells, contracting. So at any rate, so yes, sensory information, but even thinking about certain things, right, that can influence the autonomic nervous system. And that's through the hypothalamus. So all these regions, the hypothalamus just has so many inputs and outputs, but ultimately goes down to the spinal cord and the brainstem and drives these autonomic neurons. Okay. And that's what we're focusing on today, again, the actual anatomy. So in terms of the autonomic nervous system, you're well versed in that there's a parasympathetic nervous system and a sympathetic nervous system. And the enteric nervous system, you will talk about in your GI module quite a bit in physiology, but we talked about Auerbach's plexus and Meissner's plexus, right? So those don't even need input from the autonomic sympathetic or parasympathetic nervous system from higher centers. Individuals with spinal cord injury, they're still able to move contents through their GI tract, and it's because of the enteric nervous system. Okay, so sympathetic nervous system, parasympathetic nervous system, right? So just modulating between really using a lot of energy and conserving energy. So fight or flight, that term was coined, I think it was Cannon many, many years ago, to sort of talk about this, reference this period where it's a very stressful situation. You want to divert blood to skeletal muscle, maybe increase heart rate, for example. Parasympathetic nervous system, hopefully you're all in that parasympathetic state. post-lunch, hanging out in neuroanatomy class. Okay. All right. So that's what we're going to be talking about today, the parasympathetic nervous system and the sympathetic nervous system. Okay. So for both the parasympathetic and sympathetic nervous systems, we have a 2-neuron chain. So there's one neuron that's within the central nervous system. So again, this is similarities between the sympathetic and the parasympathetic nervous system. So the first neuron for both will be within the central nervous system. Okay? And then what you can see, we have an axon that's going to leave the central nervous system. And what you can see is that this is a myelinated axon, and this axon passes to a ganglion. So at this point in the course, we know that a ganglion is a collection of cell bodies in the peripheral nervous system. And that gives this axon its name, the axon of our first neuron, right? It's called the preganglionic fiber because it's before this, which is the ganglion. So we have a myelinated axon passing to a ganglion. This ganglion, it's either, again, a sympathetic ganglion or a parasympathetic ganglion. So here, this is either a sympathetic ganglion cell or a parasympathetic ganglion cell. And what we can see is that we have an unmyelinated axon. This is beyond the ganglion, so it's called a postganglionic fiber. So this is a postganglionic fiber, and that's passing to the target. So as we go through both the sympathetic and the parasympathetic nervous systems, we're going to be talking about where's the first neuron and where's that second neuron. Where's the first neuron within the central nervous system and where's the second neuron within the periphery? Okay, so we're going to start with the parasympathetic nervous system. Okay. So we're going to look, as I mentioned, we're going to focus on where's the soma of the first neuron. It's in the central nervous system. Where specifically is the soma of the second neuron? Where in the peripheral nervous system? And actually, it's the parasympathetic nervous system. I'm not going to talk about too much today because we're going to focus on it with the cranial nerves. We're going to actually spend a fair amount of time talking about the parasympathetic nervous system with the cranial nerves. And that's because, what do we see? We see that it's associated with cranial nerves 3, 7, 9, and 10. So when we talk about 3, 7, 9, and 10, we're going to be talking about the parasympathetic nervous system. So as we look up in the brainstem, right, so here we're looking at an image of the central nervous system with the brainstem, and this here represents the spinal cord. And again, what I'm putting down here is just the same idea. So what are we looking at? We're looking at where's the cell body of the preganglionic parasympathetic neuron. Again, it's in the central nervous system. And so what we can see here, sorry about that, is that within here, the brainstem, we have these nuclei, or this is representing neurons associated with 3, 7, 9, and 10. What we're going to see is that cranial nerve 3 passes to the head, cranial nerve 7 passes to various structures in the head, and cranial nerve 9 also passes to the head. Cranial nerve 10 is the vagus nerve, and what we can see here is it's passing to thoracic and abdominal structures. Okay. So when we look now at the postganglionic neuron, right? So the preganglionic neuron is going to pass to some ganglion. So in neuroanatomy, in the cranial nerve portion of neuroanatomy, we're going to talk about the specific ganglion. So here, what we can see is that they're labeling a couple of different ganglia. Right? These are all in the head. So that's what I was just mentioning, that we have various named ganglia in the head. Again, I put an example here, but we're going to learn about this when we talk about the various cranial nerves. So the otoganglion, which is this little one right here, ultimately provides this one right here provides parasympathetic innervation to the parotid gland. So that's just an example, but we're going to go through that specific pathway later. Okay, so that's where most of our focus is going to be when we talk about cranial nerves, when we talk about 3, 7, and 9. And then cranial nerve 10 does not have a ganglion up in the head. Instead, these are preganglionic parasympathetic fibers that pass to the organ itself. So we'll talk a little bit about these in gross anatomy, but what's being represented here is that the preganglionic fiber passes to the organ itself, and then within the target organ there are ganglion cells. So these would be like Meissner's plexus and Auerbach's plexus. So they do get input from the vagus nerve, from cranial nerve 10, but they can fire on their own, as I mentioned. Okay, so that's the parasympathetic nervous system. So what I want you to know is that for the most part is that it's associated with cranial nerves 3, 7, 9, and 10. We have a neuron within the central nervous system, within the brainstem, and then we have a ganglion in the periphery, and we're going to name those ganglia when we talk about the specific cranial nerves, 3, 7, 9, and 10. Okay. So this afternoon we're going to spend, well, not a lot of time talking about the autonomic nervous system, but we are going to spend more time talking about the sympathetic nervous system. Okay. So we're going to start, as we did previously, where is the neuron, the cell body of the neuron within the central nervous system, and then we'll talk about where's the neuron where's the cell body of the neuron in the peripheral nervous system. So it's in some ganglion. Okay, so when we were talking last week, we talked about the lateral horn of the spinal cord. So the lateral horn of the spinal cord is only located in thoracic and upper lumbar levels. So depending upon the source, you'll see T1 to either L2 or L3. Your textbook uses L3, so I put it here. But you might see a resource that says L2. So within the lateral horn of the spinal cord, we have cell bodies, right? These sympathetic neurons that are neurons of the sympathetic nervous system. So these are that first neuron. So that's what's being represented here. Within the lateral horn, we have a neuron. It's obviously within the central nervous system because it's spinal cord. And the axon that leaves is myelinated, and it's going to go to a ganglion. And that's what's being represented here. So we know that the axon of neurons leave the ventral horn, and what this is illustrating for us is that it's passing to a sympathetic ganglion. The sympathetic ganglia are distributed in many different locations. So that's what we're going to talk about now. So where are these sympathetic ganglia? Okay. So the sympathetic ganglia, some of them are in what's called the sympathetic chain. So that's what's being represented here. What happens to this first neuron? Right? The axon leaves the lateral horn and goes to a ganglion. Okay? And so what we're looking at here is a neuron within the lateral horn. So we can see that at several spinal cord levels. And then on either side of the lateral of the spinal cord, we have what's called a sympathetic chain. So what we can see here is that in this upper panel, this preganglionic sympathetic fiber leaves the anterior horn and it passes into the sympathetic chain at the same level. So again, this preganglionic, right, sympathetic fiber, it can leave the central nervous system, or it does leave the central nervous system. And as I mentioned, it can do one of many things. And one of the things that it can do is it can synapse in this ganglion at the same level, right? This chain of ganglia. What can also happen is that this preganglionic sympathetic fiber can enter this sympathetic chain and it can ascend to a different level. Or 3 is it can, actually let me just leave it at that. So it can ascend And it can also descend. So it can ascend or descend within this sympathetic chain. And before I
Oh
go
my
to
God,
3,
my
let me
neck.
just show
What
you
the
the
fuck?
sympathetic chain here. So as we look at actually this image, so this is the spinal cord, and you can see that the sympathetic chain is outside of the central nervous system. And we'll actually see the sympathetic chain in the gross anatomy lab. So let me just orient you to this particular image. So what we're looking at here, well, we're looking at the ribs posteriorly. So what's happened here? Well, the heart's been taken out, the lungs have been taken out, the anterior thoracic wall, all the muscles that contribute to the anterior thoracic wall, the heart and the lungs. And so what do we see back here? Well, this is the esophagus, right? So this is the esophagus passing through the diaphragm. So we're very far posterior. And we also see a bit of the aorta here. So what we can see is right along the bony vertebral column, we can see the sympathetic chain. So sympathetic chain, what you're looking at is a chain of ganglia. So when I think of these, I think of like almost like a chain link fence, right? You have maybe if these are a string of pearls or something, each prominence, each ganglion, right, would be a pearl, and then the string between them would be communicating between, the ganglia or one pearl and the next one. So at any rate, these are the ganglia, right, within that peripheral nervous system. So at any rate, what we're looking at here is that preganglionic sympathetic fiber, again, can either pass to the ganglion synapse at that level, or it can go up or down to synapse at a ganglion at a different level. So I'll come back to that concept in a little bit. So at any rate, these preganglionic sympathetic fibers can synapse in the sympathetic chain, or they can go right through the sympathetic chain without synapsing. So what we're looking at here is that the preganglionic sympathetic fiber, it goes right through the sympathetic chain, but does not synapse, and it finds another ganglion. And the other ganglion that it finds is called the prevertebral ganglion. So what's in red here is what we just talked about. What happens to that preganglionic sympathetic fiber, right? How it travels either to the sympathetic chain at the same level, goes up or down the sympathetic chain to get to a ganglion above or below, or it goes right through the sympathetic chain without synapsing. So those are sort of our 3 options of these neurons that leave the lateral horn of the spinal cord. Yes?
Are the neurons in the chain myelinated still?
So the neurons within the chain, their axons are unmyelinated. So the axons, and the nice thing about the autonomic nervous system is that we see the same thing for sympathetic and parasympathetic. So here we're looking at, let's see here, just the first neuron here, this is myelinated. You were asking about the neuron in the sympathetic chain, which would be this one, which is in the peripheral nervous system. And the axon of this neuron is unmyelinated. So the first neuron's always myelinated, the second neuron's always unmyelinated.
So even if it's ascending or descending, that's unmyelinated?
Oh, the ones that are ascending or descending, those are myelinated, because that's the first one. So this one, I'm sorry, then I misunderstood your question. This is the first neuron, and this is myelinated. When it leaves the sympathetic, like the ones that are going to leave the sympathetic chain, those will be the ones that are in the sympathetic chain and leaving, those are unmyelinated. But the ones that are ascending, maybe I misunderstood your question, the ones that enter, and if they're ascending or descending, if it's the axon of the first neuron, it's myelinated. Yeah. Okay. So here we are looking at the ganglion cells. And so as I mentioned, they are in the sympathetic chain, right? Or they are in these prevertebral ganglia. Okay. So here we're looking at an image of where these postganglionic sympathetic fibers pass. Yeah.
Sorry, I just wanted to jump back real quick. If the preganglionic fiber is ascending or descending, will it always synapse in the sympathetic chain? Or could it also leave at a different level?
So the ones that are ascending or descending, they will synapse in the sympathetic chain. So the ones that, and as we look at, and so sort of a perfect question here, what we can see is that here we're looking at the lateral horn of the spinal cord, right? Here we're looking at the lateral horn of the spinal cord. So what we can see is that the sympathetic fibers here are associated with the lateral horn of the spinal cord. These fibers are leaving, so they can synapse at that level, but we have, and this is what's particularly important for you as future dentists, these first neurons leave, and in order to get anything up to this sort of upper ganglion, it has to ascend. And this ganglion that we'll talk about in just a moment, this upper ganglion, we'll talk about it in gross anatomy, this provides all of the sympathetics to the head. So what you can see here is that all of the sympathetics to the head, they come, those axons leave the lateral horn of the spinal cord at the thoracic levels, and then they come up to what's called the superior cervical ganglion. Okay. Okay, so here we can see just the course of these passing to that sympathetic chain. So that's all I wanted to show you on this particular image, that we have these neurons that are, again, synapsing at this level, at the same level. They can ascend, they can also descend, and these here, where you can see this solid line represents the fact that these are passing right through the sympathetic chain. They pass right through, and then they course to their destination. So we will see these, actually can identify these nerves in the gross anatomy lab because they just come out and they're heading generally to organs in the abdomen. Yeah?
On this slide before, it says sympathetic trunk. Does that mean the same thing?
Oh, yeah. The sympathetic chain and the sympathetic trunk are the same. Oh, right. This term here, yes. So sympathetic chain, sympathetic trunk. Okay, so the question is, the ones that pass, right, so what we've said, they either go to the sympathetic chain or they go to some ganglion. Okay? And here we can see the names of those ganglia. These ganglia that I've just circled here, these are the prevertebral ganglia. So this represents the prevertebral ganglia. Okay. And then what we can see in this particular image is that from these prevertebral ganglia, we have postganglionic sympathetic fibers that are passing to these various organs within mainly the thoracic and abdominal cavities. So where are these prevertebral ganglia? Well, they're here right in the abdomen. So we can see them sort of represented here. They're the celiac ganglion, the superior mesenteric ganglion, and the inferior mesenteric ganglion. We are going to be very comfortable with these ganglia in gross anatomy because we're going to see them in the abdomen. And what we're going to see is that there are same named arteries around these ganglia. So in terms of just memorizing these names, I want you to know prevertebral ganglia, but by the time your first year of dental school is over, you're going to be very comfortable with those. So I'm not going to put those specifically, these names specifically on the exam. You'll hear all about them next semester because they're in the abdomen. We're going to see them. But just understand that we have these prevertebral ganglia. Why are they called prevertebral? Well, here's the vertebral column, and they sit right on, just anterior to the vertebral column. Sometimes they're called pre-aortic because they have an association with the abdominal aorta as well. So, you can see that term right here, pre-aortic or prevertebral. just in front of the aorta, just in front of the vertebra. Okay, so in terms of the sympathetics, just as a summary, this first neuron, right, is in the lateral horn of the spinal cord. It leaves the lateral horn of the spinal cord. It is a myelinated axon, and it enters the sympathetic chain. It can either synapse in the sympathetic chain at that level, it can synapse in the sympathetic chain above, or it can synapse in the sympathetic chain below. And then the postganglionic fiber goes off to its target somewhere in the abdomen. So again, we'll look at those abdominal targets in gross anatomy. The other thing, as I mentioned, that can happen is that this preganglionic fiber can pass right through the ganglion and synapse in one of those prevertebral ganglia.
Prevertebral ganglia.
So the last point that does anyone have any questions about that? Okay. The last point that I want to make, I'm going to come back to this slide here. So what we can see is that the distribution, right, of the parasympathetic nervous system, again, it's super important for you because it goes to lots of structures in the head. So this is what we're going to spend most of our time talking about. And then, of course, the parasympathetic nervous system goes to organs, thoracic and abdominal and pelvic organs. Okay. The sympathetic nervous system has much more widespread distribution. And I want to make the point that the sympathetic nervous system passes out to all smooth muscles and glands, like in the periphery. So when we think about the parasympathetic nervous system, it does not provide fibers. There are no parasympathetic fibers to the limbs. Only the sympathetic fibers. So if your hair stands up, right, that's the sympathetic nervous system. If you sweat, that's the sympathetic nervous system. It's not under control of the parasympathetic nervous system. It's just sympathetic. Your fingers get cold and you have vasoconstriction, or it's a very hot day and you have vasodilation of the skin. That's all sympathetic nervous system. It's the sympathetic nervous system. Again, you can see it's traveling up and down that sympathetic chain, and that allows it to be distributed all of the peripheral nerves that are heading out to the body wall and to the extremities. Okay? And again, just to contrast that to the parasympathetic nervous system, the parasympathetic nervous system does not go out to the body wall, it does not go to the extremities. Okay, so that's, again, a very sort of general, brief introduction. Again, just knowing first neuron, second neuron, central nervous system for the first neuron, peripheral nervous system for the second neuron, and we're going to fill in those gaps as we talk about the cranial nerves in particular. And we'll fill some of the blanks in next semester in gross anatomy as well. Anything that goes down to the thorax and the abdomen, we're going to focus in on next semester.
This is so confusing. At least this one was a short one.
I have a couple slides in here, preview of clinical cases. So before, I guess we've had clinical cases for many years. I've had these clinical cases, and you'll see it in the schedule. There's like little blocks of time, and it says clinical cases. So starting during COVID, we did all of those in breakout rooms, and I ended up giving a little bit of extra credit for people that passed them in. So I will do the same. It's just like a point you know, it goes on that like 1 or 2 points, there'll be a couple of them, will go on to your exam score. So, you know, when you get your exam soft score, if you get an 85 and you get, you know, it's an 85 will go out, but then in my spreadsheet, I'll keep track of, you know, if you get 2 extra points. Okay. The thing is that everyone should be doing those because you can't, there will be clinical cases on the exam, and so everyone should be doing those. And so it's just a way to make sure, kind of giving you a little extra credit for like actually doing them and writing them out. Okay. So what are the clinical cases going to look like? Well, they're going to look like something like this. So one of the clinical cases is Brown-Séquard syndrome. It's an actual clinical syndrome. We're going to look at a sort of patient with Brown-Séquard syndrome. We're going to look at this case with the pain and temperature pathway, the touch and pressure pathway, and the motor pathway as well, because we'll see that patients with Brown-Séquard syndrome actually have like a disassociation of some of their symptoms. So they might have changes in, you know, one sensory modality on one side of the body, another sensory modality on the other side of the body. So it's a really interesting clinical condition, and it's worth, I think, going through. So what is Brown-Séquard syndrome? Well, it's hemisection of the spinal cord. So these are more, you know, often associated with stab wounds. You know, our patient is going to have a perfect hemisection of the spinal cord. Rarely is it a perfect hemisection, but again, it will make the point that we want to make. So here we can see various spinal cord cross sections. So what you can imagine is that there's just a razor blade thin lesion through just a little bit of the, you know, through halfway through the spinal cord in the horizontal or that transverse plane. Okay. So that's a Brown-Séquard lesion. So we'll look at what happens with pain and temperature there. This is to pique your interest in doing those clinical cases. And then syringomyelia. So this is another clinical condition where I mentioned the central canal. Yeah, I did mention the central canal of the spinal cord, and it extends from the ventricles, and it can enlarge, right? So cerebral spinal fluid can get pushed into this region, and specifically what can get damaged early on are these fibers that are right here, just along the anterior aspect of the central canal of the spinal cord. So we'll see what fibers are passing in this region, but at any rate, that's a clinical condition called syringomyelia. And here, and actually what we usually see is syringomyelia, right? The fluid gets pushed down from above, right? So it's like the ventricular fluid gets pushed down from above. It can't flow out of the core of the brain and the brainstem and the spinal cord.
Sounds painful.
Okay. So we'll look at a case like that. And does anybody know what this structure is? This would be a tough one. This is called the internal capsule. So this is a structure that did someone say it up there? So this is the internal capsule. So what kind of stain is this? It has to either be a Nissl stain or a myelin stain.
Myelin.
It's a Nissl stain. So this is a Nissl stain. So how would you know it's a Nissl stain? You know it's a Nissl stain because you know that the cortex, right? Cortex means bark, and the bark of the brain is comprised of neurons. So everything that's white in through here, this is actually the white matter. So at any rate, this is the internal capsule. So this is the internal capsule, and specifically it's the posterior limb of the internal capsule. So at any rate, we talked a little bit about the anterior limb, the genu, which is at that bend, and then this is the posterior limb. So those are 3 examples of the cases that we're going to look at, you know, after we spend a lot of time talking about the pain and temperature pathways. Okay. So we're going to start out in the periphery, and you've talked about the receptors out in the periphery. So this is just a reminder of the nociceptors and the temperature receptors out in the periphery. So we're going to start there. Then I'm going to give you an example of a neuronal chain, and then we're going to spend a lot of time talking about the pathways that are carrying pain and temperature information. Okay, so let's just look at the periphery. So whether it's a thermoreceptor or a nociceptor, so noci sort of has its word origin in hurt. So noci, sort of think of a receptor that can pick up stimuli that are painful. And so at any rate, and here you can see a free nerve ending. So this is representing a free nerve ending that's passing into the epithelium here. And in this particular image, we can just see these free nerve endings associated, in this case, with the epithelium. So we have the ability to identify temperature in the periphery with these free nerve endings. So that would be, you pick up a warm cup of coffee or something and it feels warm, or, you pick up a water bottle and it feels cool. But then we can also have noxious heat and cold. So we have non-noxious thermal receptors. We have receptors that can pick up non-noxious heat and cold. We also have thermal nociceptors that pick up noxious heat and cold. There are also mechanical nociceptors. So you drop something on your toe, that would be like a crushing pain, or it's a paper cut, right? So that's, you can tell the difference between like a crushing pain, a cutting pain, burning your hand, and you're able to identify where it is. So we've got different receptors out in the periphery, so we're able to identify the nature as well as the location of the sensory stimulus, so we'll talk a little bit about that. So we have these actual stimuli that either are potentially causing tissue damage or do cause tissue damage. And once we have any type of tissue damage, then we have chemicals that are released, and these can also stimulate nociceptors, right? So all of these elements you've learned about in other courses. I'm not going to ask you specifically about the various chemicals. Those you're covering in other courses. But I'm sure they all look familiar to you. So so we have some type of
Absolutely.
stimulation of these nociceptors or thermoreceptors out in the periphery. And the types of fibers, and you've talked about primary afferent fibers, right? You've talked about this in physiology, that then these axons, right, out here in the periphery, they can carry an action potential. So if that's in my hand and I touch a hot stove, there's going to be an action potential that's carried along one of these fibers. So we have two types of fibers in the periphery that can carry this nociceptive information. So if I touch a hot stove, right, that what is often referred to as first pain, and so maybe you use that term in physiology, that first pain, it's a sharp, well-localized nociceptive information that's carried by an A delta fiber, and then a C fiber carries the dull, achy, less well-localized nociceptive information. And so maybe you've had the experience where, right, you maybe drop something on your hand and it's like localized, and then the whole thing throbs, right? So a couple of summers ago, I was camping, and I was sitting in front of a fire with flip-flops on, which is a really bad idea. So haven't done that since. And an ember popped out, and it was dark. And at the time, I remember thinking that happened like right between my first and second toe. But then within a couple of seconds, I had no idea. Like my whole foot throbbed. I'm like pouring water on it. And anyway, the next morning I woke up and my foot was throbbing, and I looked between my first and second toe, and there was the blister. But I, like, just for a split second, I knew where it was, but then there was chemical and tissue damage, and the whole thing throbbed. And so, and that's going to be important for your patients when you think about like where if they're able to localize pain, we'll actually do that in one of the IPSs.
Huh.
But that A delta pain, so what we're going to see is that information goes to different parts of the brain, and that's why it's important. So the A delta pain, we don't talk about fiber types too much in this course. That's really in the domain of physiology, but it's related to how the pathway travels up to the brain. So the A delta nociceptive information goes to a different part of the brain, the part of the brain that has a very specific map on it, whereas that C fiber nociceptive information doesn't go to the same region of the brain. So at any rate, we have these A delta fibers in the periphery. These are lightly myelinated fibers, and C fibers are unmyelinated.
Yo, hello Sam, how are you?
And then we have these polymodal
Good
nociceptors.
morning.
Again, receptors that they're associated with C fibers, but they can respond to several different stimuli. And I always feel like this is more in the domain of physiology, but it's the A delta and C fibers. I do like this image where you can see that the C fibers are unmyelinated and the A delta fibers are lightly myelinated. So the only thing I want you to know from this image is what's in the red text here. C fibers.
You're in class right
ping
now?
and
Me
temperature,
too.
prenerve endings, right?
Well,
They're unmyelinated.
I'm
A delta
rewatching a
fibers,
class.
They're lightly myelinated. Because the A delta
But
fibers
basically
are lightly
me too.
myelinated, this is that first
We're
pain,
in
that
it
sharp
together.
localized pain. It carries an action potential faster. The C fiber pain is often described as the second pain because it's slower. Those axons are unmyelinated. So as we're talking about pain, we're focusing on pain and temperature as we're talking about these A delta and C fibers and how they travel into the central nervous system. But I do want to just mention very briefly that C fibers also can carry some non-noxious sensory information. It is not the fibers that are, let's say you need to find a pencil in your backpack, or you need to find a paper clip, or maybe you have a pin
algebra,
or something in your backpack,
math.
and you're just feeling around for it, right? That's not going to be the C fibers. That's going to be a different fiber type. The real
It's
specific
like so
light touch
much,
is not these
but
C fibers, but it
like
can
at
carry
least
some
science is
general
okay to deal
sensations
with.
and things like
I could not deal with 3
stretch and
hours of math.
squeeze, right? They're not noxious, but they're a more vague sensory stimulation. Also itch, right? So you would think itch is kind of like an irritation, right? That's kind of almost like a kind of pain, something that's itchy, it's uncomfortable. That's also carried by C fibers. Okay, so we do spend a fair amount of time on pain.
So I took
in
a
this
science
course, the
master's degree
nociception. Pain is
because I can't do
technically
math.
one's experience of that the sort of nociceptive stimulus. Nociception is like, if we're going to be really particular, is the actual stimulus out
Coffee
here.
is making
and
you
then
stay
our
awake.
perception is pain.
Cheers.
But those
I have
terms,
my
and I use
coffee
them
as well.
interchangeably as well. Those terms kind of get,
It's my ASMR.
you know, I don't think we need to be quite as specific with them. We can say pain or nociception.
I'm sorry you
It's
went to my stream to try to get
complicated,
away
right?
from
Because,
class,
you know,
only
you
to
have
find
an
out that there's more
emotional
class.
response to nociception, right? Emotional response to pain or a heightened attention to pain. So people with chronic pain, for example, there's such a heightened attention that they can't pay attention, like in school or at work.
It's me.
Again, just an emotional
I'm always in
response as
chronic
well.
pain.
So there are lots of, as I have here, downstream effects, which makes pain processing really complicated. The most basic is just withdrawal, right? So, and you've talked about reflexes in physiology. We will talk about the conscious perception of pain and the pathway
Suffering.
up to the brain. We'll
At least
talk
you
a
get to
little
talk
bit
to me.
about one's
Aww.
attention to pain.
I hope we've been
And then
having
there are
a
behavioral
good set of
changes
weeks.
that are associated with nociception.
Thanks for stopping
And I
by.
mentioned the amygdala. And you think about over the course of evolution how
I
important it is.
appreciate
If you do
you.
something, you go somewhere, an animal does something, and they're injured, they will avoid that, right? So again, behavioral changes to avoid that stimulus, really important. Again, thinking about over the course of evolution. And we will also talk about the suffering, the part of the brain that's associated with the suffering in some of the emotional
I'm gonna
emotions
triple
associated with
underline
pain.
suffering.
So that's really what makes
Yes. Suffering.
pain, I think, complicated. Okay, I put this in here for fun.
It's a big one.
You have this. Do you have this slide? I think you have this slide. So I do have that. You're not responsible for this. But did you talk about TRPV1 receptors at all in other courses? Okay, so these are the receptors, right? These are the receptors that respond to temperature, right? To hot temperature.
I'm not paying attention.
And
If I
we
don't have to
also
notice for the
have
exam, I'm not paying
TRPV1
attention.
receptors in the oral cavity, and that's what bind to caspacin, so that's why those foods feel really hot. And what I think is kind of cool, and why I put this in here, is that birds do not have TRPV1 receptors, but mammals do. So if you ever go, one of the complications of feeding the birds is that the squirrels will eat the bird seed. And a lot of people don't want to feed
You
the
get
squirrels. They wanna feed the
culinary
birds.
skills? That's
And
so cool. You
can
get a cooking
actually
class? What the heck?
Bird seed with caspacin in it because the birds don't
Is this university?
feel the heat in their oral
I don't
cavity,
remember.
but the
Oh wait,
squirrels do.
you're like
mammals
secondary,
have
aren't
these,
you?
TRPV1
I still didn't have
receptors,
any
but
cool
birds
stuff in
don't. So
secondary.
anyway, when you
Honestly,
see this,
American schools
in
sort
the
of
grocery
suck
store,
because they
that's
don't give
why.
you
So
that stuff anymore.
if you have a problem
They're
with
supposed to
big
give
fat
you a lot
squirrels
of
in your
like
yard,
life skill classes,
that's what you can do.
and then they
Oh,
don't.
and you probably
Or
talked
at
about
least
this
the
in
ones
other
that I
courses,
went
but
to.
when we put cool things
Like
in our mouth,
I never
like
learned about
toothpaste, right?
I
Feels
never learned about
cool.
like
That's a
culinary or
different,
woodworking.
receptor.
I feel
But
like
the TRPM8
I feel like those would have been
receptors
actually
allows
useful
us
to know
feel
at a
cool when
base
we brush
level.
our teeth or we chew certain types of gum. So
Literally, I just
okay,
like throw
so
shit in the
at any rate,
microwave
that's just an aside that we have these various receptors.
because I'm too
and then
tired to
also
make
within the oral
food.
cavity.
One day I'll have time to learn how to
Okay,
cook.
so I know you've had
Maybe.
physiology, I know you've
I don't
talked a
know.
little bit about neuronal chains, but I just want to make sure we all are using the correct terminology because we're going to be using these terms over and over again. What I want to make the point, I just noticed I've been talking for over 50 minutes. So why don't we get back together at...
It's the last year. That's still cool though. Alright,
So
skipping.
we're just talking about the neuronal chain. So we're just talking about the neuronal chain and that we have, now keep in mind, we only use this terminology for sensory pathways. So when we talk about motor pathways, we will not be using this terminology. So just to make sure we're all on the same page, because I'll use these terms over and over again, that we have this chain of neurons that ultimately will go up to the cortex. So the pathways that we're starting with are pathways that are passing up to the cortex so that we can identify the specific nature and the location of the sensory stimulus. So the first neuron, what you can see here is that this is a region of the skin. So they're just showing a neuron associated with the skin or the terminal, the axon here. There's some stimulus. This neuron can carry an action potential into the central nervous system. This neuron that passes from the periphery into the dorsal horn of the spinal cord, this is our first order neuron. The other term that we can use is a primary afferent fiber. So primary afferent fiber or first order neuron. And the other point that I've indicated here on the slide is that this neuron, right, the axon of this neuron,
Out of coffee, you gotta refill,
it's
dude.
ipsilateral, right? It begins on one side, it ends on the
Does
same
your-
side. So it
does your
stays on the
cafeteria
same
sell
side, so
coffee?
it's ipsilateral.
Or
right?
do
It doesn't
you-
cross.
Are you lucky enough to have
What we can see
a
is that then
vending
there's
machine?
communication with a second order neuron or a secondary neuron. Okay? And what we can see is that this neuron crosses to the contralateral side. So this is a second order neuron, a secondary neuron. In this case, it's passing up to this region, which is the thalamus. So it passes up to the thalamus. And then within the thalamus, we have a third order neuron that's passing up to the cortex.
Dorsal horn.
So we could have a pathway where we have 4 neurons, a fourth order neuron, but in this case, you can see that there's these 3 neurons that are shown. The last point that I want to make is that this third neuron here, right? It begins and ends on the same side, right? So its axonal projection is ipsilateral, but the pathway is contralateral. And most often what we're interested in is the pathway. What side of the brain does it go up to? So in this case, we've got stimulation
You
of
made
the
it.
skin on
Oh,
one side, and
no.
that information is being processed
Oh,
by the other side of the
no.
brain. So it was the second order neuron in this example that crosses
Well, it's
to the
all over,
opposite,
right?
the contralateral side.
How much more time do you have
So
in
we're actually
school?
going to see that quite a bit, that this is the second order neuron that very commonly will cross to the contralateral side.
Honestly,
Okay.
I make coffee for class sometimes. I'll make coffee for class sometimes, and like I'll literally run out after the first hour, you know? And the thing is that like I don't know what you use, but I use a Keurig, and luckily like my Keurig is nice and it has like multiple options on like how much liquid ounces you want to use or like get. But the thing is that just by the nature of the Keurig and stuff like that, if you can only have up to like 12 ounces of coffee. But to be honest, I only do 10 ounces of coffee because 12 ounces plus the creamer, it dilutes the hell out of the coffee. So then it just becomes like I'm drinking water. So yeah, I only drink like around 10 ounces of coffee whenever I make it, which is nice, but then I run out after like the first hour.
So we've done enough background information. Now we're going to talk about the first pathway that's carrying pain and temperature information from the extremities and trunk. This pathway is called the anterior lateral pathway or the anterior lateral system. The anterior lateral system includes several different tracks, but I first want to give you a sense of why all of these together are called the anterior lateral system or the anterior lateral pathway. And essentially, it's named for its location, right? So what we're going to see is that the axons that are carrying pain and temperature information are in the anterior lateral aspect of the spinal cord, and then an anterior lateral
These are
aspect of a
hard.
portion of the brainstem that we talked about the other day.
This is hard.
So it's named for the location. So the anterior lateral pathway, again, it's
I forgot.
mainly we're thinking
I forgot
of
you're.
pain and temperature and some
Wait,
of
what?
these crude
What's the time zone for
sensations,
you?
like the stretch and the squeeze. And
Is that the CST?
the
Is that CST for
pathway
you?
travels in the spinal cord
Kyo.
of the brainstem.
I'm just did that.
And what we're going to see is that the axons of
Wait.
second-order neurons travel in
Who
the
redeemed that? I just heard that.
lateral aspect of
Fuck.
the spinal cord. So
Scared the hell out of me.
anterior lateral system, anterior lateral aspect of the spinal cord, as well as the anterior lateral aspect, I don't know, sorry about that, anterior lateral aspect of the tegmentum. So that, I mentioned the tegmentum last week. Actually, let me get rid of that. I mentioned the tegmentum last week, and I mentioned that it was I showed you this image, and we sort of looked at the various regions.
Oh
of the
my god,
brainstem.
there's so much material.
And we talked about this general region, the tegmentum. The only reason I even bring up that term is because when we're following pain and temperature, it's really helpful to have a general sense of where the tegmentum is. Why is it helpful? Because the anterior, these axons that contribute to the anterior lateral pathway, not only do they travel in the anterior lateral aspect of the spinal cord, but they also travel in the anterior lateral aspect of the brainstem tegmentum.
Hey,
So
it's
if
purple.
this green area
Hello.
is the
How are
brainstem
you?
tegmentum, that little bundle of axons is the anterior lateral pathway. As we move here to the
I need to go back
caudal,
and listen to this.
Sorry, the pons.
I might have to re-listen to that. That was tough. That was rough
We
writing.
talked about this general region, the tegmentum. The only reason I even bring up that term is because when we're following pain and temperature, it's really helpful to have a general sense of where the tegmentum is. Why is it helpful? Because these axons that contribute to the anterior lateral pathway, not only do they travel in the anterior lateral aspect of the spinal cord, but they also travel in the anterior lateral aspect of the brainstem tegmentum. So if this green area is the brainstem tegmentum, that little bundle of axons is the anterior lateral pathway. As we move here to the caudal, the pons, we're going to see that the anterior lateral pathway is here. And then when we get to the midbrain, it's not quite so anterior lateral, but generally you get the sense that it's certainly lateral, and in many of them, it's more anterior. So the anterior lateral pathway travels in the anterior lateral aspect generally of the spinal cord, so the anterior lateral aspect of the spinal cord and the anterior lateral aspect of the brainstem tegmentum. So someone called it the anterior lateral system. So there are a lot of words in neuroanatomy. Very often, the
Yeah,
words tell
there
us something
is.
about the pathway.
What are you learning today? I'm learning about
So
neurological
the anterior
anatomy,
lateral
which
system
is
tells us the
the
location
brain, nerves,
of the pathway,
all that
and
stuff.
specifically, we're going to see the location is location of the axons of the second order neurons.
And how am I doing?
So
I'm
it's the
doing great.
axons
I'm
of
doing
the
great. How are
second
you
order
guys doing?
neurons. So now what we can see is that the anterior lateral pathway includes location of the pathway, and specifically we're going to see the location of the axons of the second order neurons. So it's the axons of the second order neurons. So now what we can see is that the anterior lateral pathway includes many different fiber
Should I get a
tracts.
haircut today, guys? I feel like I need a haircut.
We are going to talk about the spinothalamic tract. We are going to talk about the spino-reticular
Yeah, the brain
tract, and we're going
thingy.
to talk about the spino-hypothalamic
The
tract.
thing I'm lacking.
There are other tracts that are included in here that I didn't include, like the spino-mesencephalic tract, because you talked about that in quite a bit of detail in physiology. But the ones that we're going to talk about are these that are noted here.
Ah,
Okay.
there's
So
too
I just
much.
said a whole bunch of
Too
big, long
much.
words, but the words tell us something. So when we think about the spinothalamic tract, so we're going to talk about the spinothalamic tract, which goes from the periphery up to the cortex. The spinothalamic tract, though, it's named for the beginning and end point of the second order neurons. So we're going to see that. So the axons of the second order neurons,
I have a big
where do
brain.
they
No,
begin?
my brain.
They begin
My
in the
brain.
spinal cord.
So smooth.
Where do they terminate? They terminate in the thalamus.
So smooth.
So spinothalamic tract. So when you hear spinothalamic tract, you know, number one, that is an ascending or sensory pathway, right? It's got to be sensory, and ascending is going up toward the brain.
I need
So
an
it's a
Overwatch
sensory
break.
pathway, and we know the beginning and end point of the second order neuron begins in the spinal cord, ends in the thalamus. We are going to see that there are two.
Can't you ask for extra help to
tracts.
learn? Not enough time.
Talk about
Never
two of
enough
them.
time.
We'll then move on.
just,
We'll talk about the spino-reticular tract. So
really
again,
tough.
beginning
Actually,
and
you
end
do
point
remind
of
me
the
though. I actually
second
do
order
have a
neurons,
tutor,
which
and I had to
means
text her about.
axons of
I have to text her to
spino-reticular
meet up.
tract, they begin in the
Forgot
spinal
it. Oh
cord,
my
and
goodness.
they terminate in the reticular
I forgot to text her. I
formation.
feel so bad.
And then we have spino-hypothalamic tract. These axons of the second order neurons, they begin in the spinal
I'm such a bad
cord and
texter.
they end in the hypothalamus.
Like I'll see someone
So
text
those are
me,
the three
like I'll
tracts
literally
that
see it, and I'll
actually
be like,
four,
I'll
because
text
the
her later,
spinothalamic tract has
and then I
two
don't text.
components to it. Okay. So we're going to start with the spinothalamic tract. Okay.
Particular.
So I mentioned that we have two spinothalamic tracts. We have what's called the neospinothalamic tract, and we have the paleospinothalamic tract.
Neospinothalamic tract. God damn.
A delta nociceptive information.
Neospinal. Oh my
A-delta
god.
nociceptive information,
I'm not
which
being
means
mean.
that the paleospinothalamic tract is associated
I just literally
with the
forget.
C-fiber pain.
I'm just so forgetful.
What we're going to see is that, again, when we think about the A delta, right, nociceptive information, that's going to be the sharp, right?
I barely do the
nociceptive
minimum of
information.
maintaining
And this information
necessities.
is going to pass
Like,
to
I'm so
a region of the brain called the
amazed I
primary
haven't missed any
somatosensory
deadlines.
cortex.
I barely remember to hit every
And
deadline.
It's at the level of the primary
If your hair is
somatosensory
annoying you, you should get a
cortex that we're
haircut.
able
Yeah, my hair
to
annoys me so much when it
identify
gets like
the
mildly
specific
long.
nature of the sensory stimulus, again, like a pinprick or a burn, as well as the location. Like, did you stick your finger or, burn your toe? So we'll look at this pathway. We'll also look at that paleospinal thalamic tract. And as I mentioned, this is the C fiber pathway. So this pathway is going to go to different cortical areas. Right? We're not going to have the same kind of specific map. So we're going to see that it goes to what's called the secondary somatosensory area as opposed to the primary somatosensory area. And it also goes to a cortical area called the anterior cingulate as well as the insula.
Insula.
Okay. Temperature information is carried by both the A delta and C fibers, and then itch and things like stretch and squeeze are only carried by C fibers. Okay. So now we'll go ahead. What we're going to draw out here. So what I have here in the PowerPoints, there's a handful of blank slides. So before COVID, I used to draw this on the board. We were in a different room. It would almost be impossible to draw something where everyone could see it. So anyway, during COVID, I switched to these blank slides, and we'll draw things
Having
in.
long hair and you
Okay.
like it.
So
It's
what do we
annoying
have?
to
We
me.
have
Like,
primary
I can
afferent
feel it in the
fibers.
back of, if
So
I can
in
barely
purple,
feel my
I'm
hair
going to draw in a
in the
primary
back of my
afferent
neck, it annoys me.
a delta fiber. Okay. So these primary afferent fibers, right?
I literally
Where's
cut
the
it every
cell
once in a
body?
while on my own. Like a savage. It's like in the latter horn. I don't know. I don't know, man.
It is in the periphery. So specifically, where in the periphery is the cell body? Yes. The dorsal
You're
root
already
ganglion.
confused.
The
Don't
dorsal root
feel
ganglion.
don't feel bad.
Exactly.
I'm confused and this is
So-
my class.
It's out here in the dorsal root ganglion. So it's in the periphery, it's in a ganglion, the dorsal root ganglion. So all of these primary afferent fibers, the cell bodies in the dorsal root ganglion, and then these primary afferent fibers enter the dorsal horn and they terminate. Their main synaptic site is lamina 2. So I mentioned the other day, we talked about the lamina of Rexid, right, or Rexid's laminae, and I mentioned there are 10 laminae and that we'll learn a handful of them, and one of them is lamina 2. So let's just make this lamina 2. So another name for lamina 2 is the substantia gelatinosa. So it's not the only synaptic site, but it is the major synaptic site. So that's the only one that we're going to talk about.
What the hell are we talking about?
So
Lamina substatin
bear with
2?
me, I'm using my mouse pad. So substantia gelatinosa.
What the fuck? Substantia gelatinosa.
Okay,
What?
so that's our major synaptic site. But before the axons pass into, or just as they reach the dorsal horn,
What the hell is
they
that?
can actually, we have collateral branches that can ascend
What
or
is the lamina
descend
gelatinosa?
1 to 3 segments. So they can ascend or descend 1 to 3 segments. So I have another slide in, sort of the next image, but let me just kind of fill it in here. But these can go, down to other spinal cord segments. Bless you. And this 1 to 3 segments is just anatomical variability, right? And even in the gross anatomy lab, I feel like one of the benefits of being in the gross anatomy lab is we say, this is the branching pattern of the external carotid artery. And then you look at the external carotid artery and, half of the bodies have a little bit of variability in terms of the branching pattern. So when we say that it's like 1 to 3 segments, we just have typical, normal variability. But where these axons are ascending or descending, this is called the psoas tract. So
Is this lecture
little
live?
region
It's not,
here,
it's a recording.
Right at the margin
Luckily I
of
can
the
I can
dorsal
rewind.
horn is called the psoas tract.
The what track?
So the psoas tract. Okay. And let me just show on this, not this image, I'm just going to go, okay.
The
The
source.
psoas tract. So the primary afferent fiber, let's say it comes in here. Again, the cell body would be out here in the dorsal root ganglion. These axons would also, I'm going to have to use a different color. we're going to use white, right? So just like this is, let's say this axon comes in and it synapses in lamina 2, right? This
Okay.
collateral branch could also be here and synapse in lamina 2 above, and it could ascend and synapse in lamina 2 here. So this, maybe I should just use all the same color. So let's use yellow so we can see it. But if this axon, primary afferent that's shown in yellow, it can also go up to another segment and synapse, and go up to another segment. And it travels in these propriospinal fibers. Remember I mentioned some of the lectures ago, but on
Propriospinal
Friday, I shouldn't say do you remember.
fibers.
On Friday, we talked about propriospinal fibers. What I mentioned is that there are some fibers that stay in the spinal cord. And I mentioned like when you step on a tack, right, that you have to have coordination, otherwise I'd fall to the ground if I pick up one foot. So these are propriospinal fibers because they stay in the spinal cord. So it's just a way, so again, why do we have this? Maybe over the course of evolution, it was important to get this nociceptive information to multiple spinal cord levels.
What the fuck?
With lateral inhibition, which
How do you
we've
survive
talked
this
about, we're not gonna
lecture?
talk about in this course,
I don't have a
ultimately
choice.
That gets fine-tuned, right? But it
I
does
love
diverge once it comes into the spinal
I love
cord.
that new feature with VTube
Okay.
Studio where you
So
can
that's what
spam
happens to the
emotes
first
at
order
me.
A delta fiber.
That's pretty dope,
For the
actually.
C
I love it.
fiber,
It's
we
cute.
see the same general course. We have, right, our primary afferent, right? So let's say these are the little branches out in the periphery, right? Our receptive field, all our branches. Primary afferent enters. Cell body is still in the dorsoroot ganglion. Right, these axons can also ascend or descend 1 to 3 segments in Lesueur's tract. Okay. And then these axons will enter into predominantly lamina 2, substantia gelatinosa. Okay. Okay, so that's the first order neuron. So let's go ahead and just take a look at what I call the cleaned up version. So now we can see kind of what we drew out. We can see the primary afferent fiber, the cell bodies, and the dorsoroot ganglion. Again, ascending or descending. So here's that text. It ascends or descends in Lesueur's tract. So what you can see is that Lesueur's tract, right? They're now
I realized what's
in
really
the-
funny though
the
is that
central nervous system,
you could
but it's
see
still
the
A delta
green
and C fibers.
is
It's still those,
transparent
it's a
because of
continuation of the axons
the way
were
that
out in the periphery.
my thing
So
works.
these A delta and C fibers,
It's
they
so
can ascend
funny.
or descend 1 to 3 segments, and then they pass into
Maybe I gotta fix that someday.
substantia gelatinosa into lamina 2. And it's the same thing whether it's an A delta or a C fiber. Okay.
Make it transparent. I'll
And
fix
just
that one day.
the final point about Lesueur's tract and substantia gelatinosa, here we can see it. So this is Lesueur's tract. So what you can see when we look at Lesueur's tract, it's lightly myelinated. It's lightly myelinated because we have A delta fibers, which are lightly myelinated, and C fibers, which are unmyelinated. So when we look at the amount of stain that Lesueur's tract has taken up, we can see it's much different than the amount of stain out and through here. And so maybe I should have asked, what kind of stain is this? Is it a
Nissel.
Nissl stain or a myelin stain?
I don't know at this point. Is it
Exactly,
Nissel
it's a
or
myelin
myelin?
stain,
God
right.
damn.
So you
I
can
don't know
see
the
the neurons
difference.
out and through here.
I knew
right?
it.
These are much more heavily myelinated compared to those in Lesueur's tract. Okay, and here you can see substantia gelatinosa. So substantia gelatinosa is just packed with neurons, so it doesn't take up much of the stain at all. Again, sort of the staining that you see here, right? So we do have axons that can stream through the gray matter.
Lesueur's tract formed
Okay.
by alpha.
So that's the first order neuron. What about the second order neuron? Well, what we're going to see is that the second order neurons for
Don't worry.
the second order neurons that receive the A delta
I'm just
pain,
wondering to myself.
we have one population that receives the A delta pain and another population that receives the C fiber pain. Okay. So on this slide, we'll talk about the A delta nociceptive information. Okay, so we've got the A delta fiber enters into lamina 2. And so I'm not going to draw Lesor's tract or anything, but we'll just have it coming into lamina 2. The cell bodies of the second order neurons, so that's really the focus again of this slide, is looking at the location of the second order neurons. The cell bodies of the second order neurons are located in laminas 1 and 5. Okay, so we have laminae 1 and 5. So these neurons in laminas 1 and 5, right,
Lamina 1.
they have dendrites that sort of extend. They have these wide dendritic trees, and they extend their dendrites back into lamina 2. So what I'm trying to draw here is that these are little dendrites extending back into lamina 2 so that there's communication between neurons in here in laminas 1 and 5 with the input, right, coming in to lamina 2. So essentially we have communication of neurons, right, the primary afferent fibers with neurons in laminas 1 and 5. So really the point of this is that this information, we're going to see that the C fiber pain is not associated with neurons in laminas 1 and 5. So the axons of these second order neurons, right, these then cross midline. Actually, maybe I'll use a highlighter, make it a little bit thicker. But these are the axons of the second order neurons, right? They then cross midline. So they cross midline and they pass to the anterior lateral aspect of the spinal cord. So this here is that anterior lateral system that I mentioned previously. Okay. So maybe I'll put kind of outline, right? I'll put the nucleus. I'll outline these neurons in laminas 1 and 5. I'll kind of outline them with yellow.
It looks like alien.
Here's another
It's
one.
like this is what happens when you cut the brain stem. It's our brain.
So let's look at a cleaned up version of that, right? So what we can see here,
It's
and
our
here's the
brain.
text on the slide. So what do we see? We say the primary afferent fiber, right? It's an A delta fiber. This primary afferent fiber, right? This is carrying that first pain. This is a lightly myelinated fiber, and it carries it from the periphery into the spinal cord and specifically into lamina 2 or the substantia gelatinosa. And sometimes it's helpful. You can see I have like where it begins, where it ends, where the cell body is. It's helpful to like ask yourself those questions as you're drawing out the various pathways. Like where does it begin? This one begins in the periphery. Where's the cell body in the dorsal root ganglion? Where does it end? It ends in lamina 2 in the spinal cord. Okay. And the other one is, does it cross? No, this doesn't cross. Okay. Then we have our second order neuron, so we can ask ourselves the same question. Where's the cell body? Well, the cell body is located in laminas 1
Good
and
luck.
5. That's where it begins.
11 more
Right?
minutes.
So
You
in
got
case,
this.
The location of the cell body is the location of where it begins. The other thing you can see in this image, the dotted lines are representing the dendrites. That's what I'm trying to represent here, the dendrites
Oh, God,
extending back. But at any rate, the cell bodies are in laminas 1 and 5. What happens to the axons? Well, do they cross? Yes, they cross. We haven't talked about where they terminate, but where are they going to terminate? If it's the spinothalamic tract, they're going to terminate in the
Thalamus.
thalamus because they're named for the beginning and end point of the second order neurons. Okay. So we know where they begin in the spinal cord. We know where they end in the thalamus, and yes, they cross. Okay. And so here we can see, again, another sort of cleaned up version. And here we can see first order neuron and our second order neuron. Okay. For the C fibers, we have a very similar pathway, but the second order neurons are in different laminae. So we're going to see they're in laminae 7 and 8, right? So that's where the cell bodies of our second order neurons are located. So we know the first order neurons. We know the first order neurons, the cell bodies are in the dorsal root ganglion. They pass into lamina 2, right? Now we know the location of the cell bodies of the second order neurons, which are lamina 7 and 8. So in this case, I don't want to get bogged down with interneurons, but there are little interneurons that can communicate between, neurons in lamina 2 and these neurons in lamina 7 and 8. But at any rate, we've got just communication with neurons in lamina 7, 8, and the axons of these neurons cross midline. So these neurons still cross midline, and they're going to join that anterior lateral pathway. Okay. So here's just again, sort of a cleaned up version of that where you can see, right, primary afferent fibers, they're C fibers, reminding you what they carry, so the dull, achy, less well localized nociceptive information, right? They're carrying it from the periphery into the spinal cord, okay? And then within the spinal cord, here we have our second order neurons. The second order neurons are located in laminas 7 and 8, and these cross midline. I just realized I don't think I've used the term anterior white commissure. Where these cross, that's the anterior white commissure.
You need to know that?
Okay, and they cross to the anterior lateral aspect of the spinal cord. So let's go ahead and just take a look. This is sort of the last image here. What we can see is, these axons coming in, first order neurons coming into lamina 2, and then we can see the crossing of those second order neurons. The last point that I want to make is thinking about that case that I showed you. If this is the central canal of the spinal cord, you can see why enlargement of the central canal of the spinal cord can impact these fibers first, right? Because they're right there. So as these fibers cross, they're at risk if there's enlargement of the central canal of the spinal cord. So that's what you'll be looking at when you look at that case of a patient with syringomyelia. Okay. Any questions about the first order neurons or the second order neurons? Okay. So
I don't know how to spell
now we are going
syringomyelia.
to shift from a spinal cord cross-section, and we're going to use this template many times as we talk about how the information ascends to the thalamus and then goes up to the cortex. So essentially what we're looking at here is a coronal section through the central nervous system. So we talked about the two cerebral hemispheres previously, so we're looking at the two cerebral hemispheres. We can see the thalamus bilaterally. These are some deep nuclei of the basal ganglia. So this is all gray matter that's sort of in this gray color. And then what's represented here, this is the internal capsule. So at any rate, this is the internal capsule. So then we make our way from the cerebral hemispheres down to the brainstem. So we've got the midbrain in this upper region. This bulbous portion is representing the pons, and then we've got the medulla here. So this is representing the medulla, and then all of this is representing the spinal cord. This particular image also has some cross-sections, so we started looking at cross-sections, and we'll continue looking at cross-sections today. Okay. So as we draw things out, I just put a couple of notes here because like over time I've gotten questions like this. So for the most part, we're going to draw in one neuron and one axon as we're drawing in a pathway, but I mentioned that we have 86 billion neurons, so we're going to just draw in one for simplicity, right? So of course there's never just one axon, one neuron, but for simplicity we're just going to draw in a single neuronal cell body and a single pathway. And we are also going to draw things in on one side for the most part, but of course everything, especially early on, everything that we talk about is bilateral and symmetric. So there are some parts of the central nervous system that are not bilateral and symmetric,
Ah,
but all the sensory and motor pathways that we're starting out with are all bilateral and symmetric. And even, back here when we drew this out, right, I only drew it in on one side, but of course you'd have the same exact pathway coming in on the opposite side. So just keep that in mind. And then also keep in mind that the tract, again, although admittedly very long names in many cases, they do give us information about the tract in terms of the direction of information flow, which usually tells us is it sensory or motor. So the direction of information flow, as well as something about a beginning and end point. Very often it's the second order neuron, but not always.
I'm already
In the case of these pathways, it's the second order neuron. Okay, so what are we going to do now? We're going to shift from the spinal cord cross-section and talk about how this information makes its way up to the cortex. And again, it's up at the level of the cortex that we are able to identify the nature and the location of that sensory stimulus. Okay, so any questions before we move on? Okay, so what happens to, so this is an A delta fiber, right? So I'm going to use the purple again. So we've got an A delta fiber, and we're not going to worry so much about what happens. We're not going to draw out sort of the details that we just drew out, what happens in the spinal cord, right? We've gone through that. So what do we have? We have a primary afferent fiber. We know, because you told me, that the cell body is out in the dorsal root ganglion. And we know that there's a synapse in the dorsal horn of the spinal cord. So this is representing the second order neuron. Right, so that's in laminas 1 or 5 or both. At any rate, and then we've got our second order neuron that crosses midline. So this is what we talked about up to this point. And we know that this axon is going to the thalamus because it's a spinothalamic tract. So it's the neospinothalamic tract, which is over the course of evolution, sort of more phylogenetically more recent. Paleo means older. So at any rate, this neospinothalamic tract, these axons cross midline, and they ascend through the spinal cord, through the medulla, through the pons, and through the midbrain to reach the thalamus, right? So spinothalamic. And specifically, they reach a nucleus called the VPL. So many of the thalamic nuclei, not all of them, but many of them are named for where they are. So VPL tells us a little bit about where it is. It's ventral. It's posterior. And it's lateral.
BPL. Ventral, posterior, lateral.
So recall here that ventral, right? So for the thalamus, the ventral surface of the thalamus. What's the synonym for ventral in the thalamus or the brain?
Isn't it the top? Let me steal your coffee? Dude, it's cold though. My coffee's cold at this point, bro.
Inferior. So inferior. So think of your tongue. The ventral surface of your tongue is the inferior surface of the tongue. So it's the undersurface, right? The inferior surface. It's posterior, which is the back. and it's lateral, which is away from the middle, right? So ventral posterior lateral thalamic nucleus. Okay. Then from the VPL, we've got our third order neurons sitting within the VPL, and then we've got axons that pass through the internal capsule, a specific portion
Cold
of the
coffee is
internal
nice.
capsule, and pass
Cold
up
coffee
to
is
the
nice when it's
cortex.
iced
And in
coffee.
this case, they pass up to what
You know, my Keurig has an iced coffee button, or it has iced coffee support, which I don't know what that really means. Like, it's still gonna go hot, and I'm pretty sure you need to pour it over ice. Like, it just basically, I don't know, I don't know, you need a specific iced coffee K-cup, which is maybe stronger, and then you pour it over ice, and then the ice will cool it down to iced coffee. But I feel like cold shocking it is not gonna be good, you know? Like, I feel like it's basically the same effect anyways, you know? Like, I don't think it's gonna taste good. So I've never tried iced coffee that way. I used to be such a fiend for iced coffee. I lived next to a local supermarket that sold what was the name of the brand? Oh, International Delight. It sold International Delight iced coffee, and like the mocha. I drank that so much last year. I actually really like it. I really sort of I miss that. That was really good. But they don't sell it
we
anywhere
call
else except that one market, and I don't want to go all the way there.
primary somatosensory cortex. So this region here is representing what's called the posterior limb of the internal capsule. Okay.
The what?
So posterior limb of the internal capsule. Okay. So when we were looking on those first few clinical slides, now we've talked about, right? We talked about syringomyelia, right? That enlargement of the central canal of the spinal cord, and one of the lesion sites was in the posterior limb of the internal capsule. Okay. So we'll come back to that later. Okay.
Posterior limb. Pardon?
Okay, sorry. So this right here, where these axons are going, this is the posterior limb of the internal capsule. This triangular region, this is gray matter. These are the basal ganglia. And so I will show that to you on some coronal sections and brain sections. So the internal capsule, I didn't use these words previously, but it travels between the thalamus and the basal ganglia. So I didn't use that terminology previously, but I will starting today. I think the other day I said it passes through this deep gray matter. Yeah.
Sorry, can you repeat where the posterior limb is?
Oh, yeah. So the posterior limb of the internal capsule. So this region here that I put that black circle around, this is the internal capsule. So the internal capsule is formed by white matter. So it's formed by white matter, so it's formed by axons. And actually, why don't we go back to that image? You know, this is probably a good time to go back to the posterior limb of the internal capsule. That image I'm showing you is a coronal section. But here, this is the internal capsule. Actually, you know what? Maybe I'll show you on this image. Just a...
We have gray matter in our brains. Does that mean we have superpowers?
So I'm going to show you the
Absolutely.
same general view.
Heck yeah.
So this right
We
here
have the power to do whatever we believe in.
capsule. Do you see how this is very
Onward to your next
similar to
class.
what I was
Good
just
luck with
showing you?
culinary. Don't chop
So
yourself. Don't cut yourself.
So we're getting a little ahead of ourselves. But if this, where you see those circles, this is the thalamus where I just have this yellow. This region here is some nuclei of the basal ganglia, right? So this is the thalamus here. Here's some nuclei of the basal ganglia. And what's in black between them, that's the internal capsule. So this is a myelin stain, but the myelin is black here. Okay. So we're going to, look at the internal capsule lots of times. But here on this image, so you can see that it's between the thalamus and between this region called the basal ganglia. So that's what this is representing. So we have a whole lecture on the basal ganglia, in November, I think. Okay. So what we'll do now, so again, we just went through.
Dude, Be Real's asking me to take a
we drew it
picture right
out,
now.
And the pathways
Get out of here, Be Real. I
draw
don't need
out
you.
with you in class are the pathways that I think are important for you to draw out on your own. That's why we take the time to do it. It's the pathways that you have to draw out in order to figure out a clinical case. And what you're going to see, we're going to start out with the spinal cord pathways in some of the
No
clinical
culinary?
cases, and then we're going to do the trigeminal cases, which are a little
When
bit more
culinary?
complicated. And we're going to build on it even next semester. And by the time you get into,
I got lost. I don't even know where we are right now.
of nerves in the head, it's just like
Okay.
you've done it a million times and you're so comfortable with it. But we start here with the spinal cord. So at any rate, now we're going to go through that same pathway as I mentioned in sort of a cleaned up version, and then you'll see there's various text on the slide. So what do we see? We have an A delta fiber. Again, the cell bodies in the dorsal root ganglion. This is our sharp, localized nociceptive information and temperature information. Passes into the dorsal horn of the spinal cord. It's going to synapse on neurons in laminas 1 and 5. So when we think about the neospinal thalamic tract, it's neurons in laminas 1 and 5. These axons cross midline. Where do they cross midline? That's in the anterior white commissure. So they cross midline right here in the anterior white commissure. These axons, again, they travel in a bundle in the anterior lateral aspect of the spinal cord and the anterior lateral aspect of the brainstem tegmentum. They pass up to the VPL, and then they pass through the posterior limb of the internal capsule, so you can see that word here, and then they pass up to the primary somatosensory cortex. So we'll take a look at all of that. Okay, so what did I just add here? I just added the general location of these pathways as they travel through the spinal cord and through the brainstem. So
Advisement, culinary,
look at real
chemistry, and
brainstem
marketing.
cross sections and follow this pathway. But here's the approximate
Those
location
sound sort of dope classes.
on these
Aside from
sketches of
advisement
the
and
brainstem. So I'm
chemistry.
going to leave it at that. Now
Actually,
you can sort of look
and
at
I guess
things, go back and
algebra.
study, but we will
Honestly,
look at
once you get
real
past
brainstem
algebra,
cross-sections after we go through
it sounds like
the
culinary and
C-fiber,
marketing sound cool.
pathway, the paleo
That sounds dope.
tract. Okay, so we're going to see lots of similarities as we talk about the paleospinal thalamic tract. So we've got our C fiber, right? So we've talked about that. We've got our primary afferent fiber with the cell body in the dorsal root ganglion. Right? It's going to synapse in the dorsal horn and it's going to communicate. Again, it happens to be through interneurons.
You don't understand chemistry?
Just
Yeah, me
with
too.
our
I promise.
second
It's
order
tough.
neurons that are in
That's why
laminas 7
That's
and
why I
8.
like biology more.
So is everyone with me now? This is what we talked about on the previous slide when we were drawing out the horizontal section of the spinal cord. Okay, so what happens here? The axons of the second order neurons cross midline, still spinothalamic, right? So it's paleospinothalamic, but this is still going to the thalamus. But this is going to a different region of the thalamus. The C fiber nociceptive information goes to a group of nuclei. And the group of nuclei collectively are referred to as the ILN, which stands for intralaminar
The paleospinal spinal
thalamic
thalamic.
nuclei. So it's a group of nuclei.
Isn't this the same exact thing though? Oh, this one goes into not the VPL, but the I see. I need a different color for this. The intralaminar
So you'll see on the slides in
nuclei.
gray text, I put like centromedian, and maybe you talked about that in physiology. I'm not going to ask you to memorize any of the specific names of the nuclei within this group, but it's just not a well delineated group. So it's like, when you think of laminar, right, we've talked about laminar organization, a layered organization. So these are more layered, and it includes several nuclei. At any rate, that's the synaptic site for our second order neurons of the paleospinal thalamic tract. The third order neurons still pass through the internal capsule, but they pass then to multiple cortical areas. So most of the fibers do pass through the posterior limb of the internal capsule. Those are the ones that are going to S2, our second somatosensory area that's processing pain, and the insula. So we'll look at these cortical areas. And then some fibers actually do pass through the anterior limb, but it's easy to remember because the anterior limb carries fibers that are going to the anterior cingulate cortex. Okay, so let's just look at, again, a cleaned up version here. There are the C fibers, right? Pass into the dorsal horn of the spinal cord. It's going to synapse with second order neurons. We have communication, right, with neurons in laminas 7 and 8. What we can see is these axons are going to ascend right through the brainstem to the ILN. So it's a group of nuclei. And then
They still go to the
passes
ALS?
through the internal capsule to get up to the cortex. Right? So some part of the internal capsule to get up to the cortex. And so I do have it up there, posterior limb to S2 and insula, anterior limb to the anterior cingulate. Okay. Oh, you're probably so happy. It's, okay, what time is it? Two, yeah, 2. Okay. So we'll get back together at 3:03.
303.
Okay. Yeah. It would be
What?
all right. So the next thing that we are going to do is go through some cross sections. So essentially what we're going to do very shortly is we're going to look at cross sections that starting with the spinal cord. So we just drew in fact, this is what we were just looking at. We're going to say, where are these axons when they're in the spinal cord? So we're not going through, it's new information in that we're looking at where these axons are located at these various levels. But essentially what we will do is we'll say, okay, here's a cross section of the spinal cord. Where is this pathway? Then we'll look at a cross section of the caudal medulla, and we'll say, where is the pathway? And the rostral medulla, where is the pathway in the pons? And then we'll look at the pathway in the midbrain. Then we'll look at the thalamus, and then we'll look at the internal capsule, and then we'll come up to the cortex. So when I say that just explicitly, so that when you go back and study, that you're going to see, then all of a sudden you're going to see all these cross sections. The cross sections are specifically related to the pathway.
I think I'm gonna
So we're going
cry.
to start with the spinal cord because we're going to follow the pathway up. We're going to start with the spinal cord, and then we're going to make our way through the brainstem and up. But before we do that, now this is hard. This is a hard one, but I want you to spend a minute or two, and I know, did someone just put their hands over their eyes like, oh my God, please no. Just do your best looking at these cross sections. So before you even look at the letters, right, just see
Don't
if you can
cry.
put these in order.
But I'm
And
dying.
there's a term from rostral to caudal. So then you have to know what's rostral and what's caudal. So there's
Caudal is the back of the. I actually don't know. Caudal is the bottom. Rostral is the top. Isn't it D? Oh shit. Okay. So what's the pons is the middle. It's D B. Fuck my life. D B C A. D B C A. So whatever the fuck answer C is, that's the answer.
D, which, so this is the order.
Oh my god,
D,
I actually
so
did
this
it.
is
Fuck
the-
yeah.
the
Oh my
midbrain,
god.
and I heard someone say bulbous portion of the pons, so that's the pons, and this is the fourth ventricle that sits behind it.
Oh god.
And then here we can see these are the inferior
Crying on live stream. It wouldn't be the first time, I
rostral medulla,
promise.
and then we
I
have
promise.
those 3 pairs of nuclei in the caudal medulla. So that's a hard one because we just started this. But what we're gonna, I just wanted to throw that in there because what we're gonna do now is we're gonna go through, first look at the spinal cord, then we're gonna look at the caudal medulla. Where's the pathway as we look at the rostral medulla, the pons, and then the midbrain as we make our way up. Okay. Okay. So I don't have a
Thank you.
turning point question for this, but as we look at this spinal cord cross section, if I were to ask you, just take a second and think about in the yellow sort of highlighted region are the cell bodies of these axons. So the cell bodies of the axons in the highlighted region, right, are the cell bodies ipsilateral or contralateral to this yellow region. So the cell bodies, we're looking for the cell bodies of the axons in the highlighted region.
I don't know, are they contralateral? I hope they are. So that we cross over.
Yes, contralateral. Yes, they're contralateral. So, okay, so let's just look at the pathway, right? So what did we say previously? Right, so what we said, I'm going to just erase everything, but the primary afferent fiber enters the dorsal horn of the spinal cord, synapses, right, enters into lamina 2, right? The cell body of the first order neuron is out in the dorsal root ganglion, but the axon of the second order neuron crosses midline at the anterior white commissure and then passes into this region. So the cell body is right here, right? So that's contralateral. So the cell body of the axons that are in this region are contralateral. Okay.
Contralateral.
Okay.
Sounds good to me.
So we can see where the axons were in the spinal cord. Now we're going to follow them through the brainstem. So this is the caudal medulla, and you did a great job of just identifying this as the caudal medulla, right? Because here we can see those 3 pairs of nuclei. So we see the 3 pairs of nuclei, and this myelinated region here, this is the anterior lateral pathway. So that's where we have fibers of the neo and paleo-spinal thalamic tracts. Okay, so the axons continue, right? So they're just ascending through the caudal medulla. They reach the rostral medulla, and here they are. So still in the anterior lateral aspect of
I can barely see
brainstem
that. I don't even know what I'm
tegmentum. So I
looking at.
didn't specifically show that on the previous slide, but these inferior olives are not part of the brainstem tegmentum. So this is anterior lateral. And the same thing with the caudal medulla. Like, this is not part of the brainstem tegmentum. So this is relatively anterior and lateral. So again, if you kind of just cut off that most ventral portion. When we get to the mid-pons, admittedly, this is a little small, but it's the only thing in this region. So again, we're going to just lop off the most ventral aspect of the pons, and so you can see that this is relatively anterior and lateral. So that's the anterior lateral pathway, both the paleo and neo-spinal thalamic tracts. So these are and I think I mentioned this, these are the exact same brainstem cross-sections that you'll see on the exam. And as we look at the midbrain, this is the anterior lateral pathway. Okay. So just take some time going through them, feeling comfortable with the level, and then following the various pathways. And again, when you think about what's the brainstem tegmentum, all of this is not the brainstem tegmentum, right? So again, it's not quite anterior, but it certainly is lateral. Okay, so we've just followed the pathway through the brainstem, and now we know that the axons of our second order neurons, spinothalamic, they terminate in the thalamus. So here are just a couple of images of the thalamus. So really what I'm trying to kind of illustrate here is that these axons of the second order neurons, right, they're traveling in the contralateral aspect of the spinal cord. They travel right up through the brainstem, and they're going to synapse, or they do synapse right in the thalamus. So we looked at the location of the thalamus previously on this mid-sagittal section. You can see it right where those circles are, part of the diencephalon. And on this coronal section, we can see the thalamus a bit better because on this coronal section, we can see the depth of the thalamus here. Right? So all of this is thalamus. And between the right and left thalami, we have the third ventricle. So this is the third ventricle here. So in this image, we're just looking at the most medial surface. I know I mentioned this the other day, but this is just the most medial surface of the thalamus. Right? So it's almost as if you're standing in the third ventricle and looking at this surface where I have that red. So again, just to give you a sense of where the thalamus is, it's part of the diencephalon. So like the cerebral hemispheres, I think we use the term telencephalon. We'll use that term, many times. Right? Telencephalon, where we have the cerebral hemispheres, the thalamus, and the hypothalamus are part of the diencephalon. Okay, so the second order neurons, they terminate in the contralateral thalamus. And then the third order neurons, the axons, right, the cell bodies of the third order neurons are located in the thalamus, and the axons are going to pass through the internal capsule, mainly the posterior limb of the internal capsule. So here we're looking at a horizontal section or a transverse section through the brain. One of the things that helps us identify this as a horizontal section, or this is posterior, you can see the cerebellum here. right? So we can see both sides of the cerebellum, and we can see the two cerebral hemispheres. At any rate, this is the thalamus. And so I'll put a T here for thalamus. And this other region that's colored in, these are the basal ganglia. So again, a collection of nuclei. So sort of what I'm shading in red, these are various nuclei of the basal ganglia. And so what we can see in this myelinated section is that the axons are in this sort of brownish black color, but we can see the internal capsule. We can see both the anterior limb of the internal capsule, which is this portion here, which is more anterior, what I put in yellow. And then in, let's say, light green, this is the posterior limb of the internal capsule where most of our fibers pass. And then, yeah, blue, this is the genu. So genu refers to bend. That's supposed to be blue. Genu is at the bend. Again, think of knee when you think of genu. So that's the genu. Okay, so what passes through the posterior limb of the internal capsule? What the illustrator is trying to show here is that the VPL is in green. And so what you can see is that these neurons in green are representing the VPL, the ventral posterior lateral thalamic nucleus. We can see that axons are streaming through the posterior limb of the internal capsule to get up to the cortex. So the fibers from the ILN, again, most of them go through the posterior limb of the internal capsule unless they're going to the anterior cingulate. And if they're going to the anterior cingulate, then they would go through the anterior limb of the internal capsule. So again, the anterior cingulate is in relatively anterior, and so it goes through the anterior limb. Okay. So it passes through the internal capsule.
What's the
to get to
ACC? Is that the
cortex.
anterior cingulate?
All right. So if we are able to identify
What's
right,
ACC?
sensory stimulus, whether it's at the tip of the second finger or the third finger or between, like in the web space between the first and second toe or second and third toe, it means we must have a map of the body on the primary somatosensory cortex. So it's at the primary somatosensory cortex that we're able to identify the nature and the location of the sensory stimulus, right? Before that, we're not able to, right? It has to get to the cortex. That's where we have the map of the body that allows us to identify the type of sensory information and where it is. Okay. So here we're looking at the central sulcus, and I know some of this is a bit of review from physiology, but this is the central sulcus. So we know that, we discussed this the other day, that the central sulcus separates the frontal from the parietal lobe. So everything in green here is the parietal lobe. And what we can see is that the primary somatosensory cortex is located in the parietal lobe, just behind the central sulcus. So that's what we're looking at here, is that post-central gyrus. Okay.
Post-central gyrus.
Okay, so the neospinal thalamic tract is the one that goes to the primary somatosensory cortex. So I mentioned that there's a map of the body on the primary somatosensory cortex, and that's shown in the next slide. Okay. So just a note, I just have a note here that we're able to identify the nature, right, pinprick versus a burn, but if it's the second digit, it means we've got to have a map of the hand on the primary somatosensory cortex. So here we're looking at the organization of the primary somatosensory cortex. And what we're looking at here is a coronal view. So you probably generally talked about this in physiology. We're going to just go into a little bit more detail about the mapping. And of course, it's important because we've got the face here as well, and the oral cavity is associated with a map in the primary somatosensory cortex. Okay. So what we're looking at here is a coronal section. Right? We can see a coronal section through the primary somatosensory cortex. So here's a lateral view, and they're showing, it's almost like taking a book out of the bookshelf, right? And you're taking a slice out, right? So we're going to take a slice out, and then we're going to turn it. So if the binder or the binding of the book is more lateral, you slide it out, then the pages of the book would be, where you'd open it would be more medial, right? So we just slid out a coronal section, a coronal hemisection, right? Just half of the one cerebral hemisphere, and so now we can see medial toward midline, and this is more lateral towards the outer surface of the brain. Okay, so what do we see here? Well, we see a map of the body on the primary somatosensory cortex. So generally the map, so you should generally have an idea of the map of the body on the primary somatosensory cortex. And you can see here that there are some differences in the color coding on this particular image, and that color coding we're going to come back to. It actually has a clinical relevance to it. But for our purposes now, you should know that the lower extremities are medial, right? So as we look at this, we can see that the knee sort of hangs over this bend from the dorsal surface of the brain to the medial surface of the brain. Remember, the top of the brain is the dorsal surface, so this is the top of the brain. So as we move from the medial surface to the top or dorsal surface of the brain, this is where we have the lower extremity. So I like to think of it as that the knee is at the bend, right? So here's the knee, and it's right where the brain bends from medial to dorsal. Then as we look at the way that the body is mapped onto the
Parson, thank you
primary
so much for the
somatosensory
follow.
cortex, think of someone reaching their arm up
I
towards
appreciate
the
you so
ceiling,
much.
or like doing the backstroke, right? But their head is displaced to the fingertips. So it's like a headless person reaching up to the ceiling, and then their head is displaced. So what we can see is that we've got, the trunk, and then you've got the shoulders, arm, forearm, and then you've got lots of representation of the hand, and then the face is lateral, coming down into sort of the pharynx, etc.
Medial lateral.
So that's the general map. But what you can certainly see that I haven't pointed out, but what you can see is we don't have a one-to-one representation. And as you look at the map here in these two images, what you see is that there's more cortical area extracting information from regions that are more sensitive, right? So from the regions of the face, particularly the regions around the oral cavity, and then the hands, right? So we have much more cortical surface area that's extracting information from the hands and the face in general. And so you've talked a little bit about that in physiology. You talked about receptive fields and that sort of thing. So that's like directly related to the mapping on the cortex. Okay, so let's just talk a little bit about the information that's going to other cortical areas. And I just want to come back to this Brodmann's map. So as we look at Brodmann's map here, primary somatosensory cortex, areas 1, 2, and 3 here. So as we look at the secondary sensory areas, it's just helpful to kind of have a sense of where the primary somatosensory cortex is. And again, here you can see it drops onto the medial aspect of the brain as well. Okay. So what about so that was the neo-spinal thalamic tract, right? So only when we were just talking about primary somatosensory cortex, right? This is only that A delta nociceptive information, the neo-spinal thalamic tract. So what about that C fiber nociceptive information? Well, that information, as we said, goes to numerous areas, right? So these areas, right, are what we perceive with this nociceptive information going to S2, the insula, and the anterior cingulate, is that it's dull, achy, less well localized nociceptive inflammation. Okay.
Anterior
And we'll
singular
also
cortex.
talk about sort of the emotional response to pain and the suffering associated with pain. But first for the S2 region, okay? So we have a secondary somatosensory area for pain. This is not the same secondary somatosensory area for touch and pressure. We'll talk about that later, but this is a secondary somatosensory area for pain. And here we can see that it's just posterior or caudal to the primary somatosensory cortex. So again, the primary somatosensory cortex would be here where I just put that red line. So there is somatotopic organization of S2, but it's not as specific as S1. So we don't have the same kind of map, right? So this area, so maybe it's like the whole forefoot or most of the foot, right? That's going to be irritated, right, if we're stimulating this region of the cortex. It would be painful if we're stimulating this region of the cortex. So at any rate, pain goes to, nociceptive information goes to S2. It also passes to the insula. So the insula got its name because it's insulated, right? What do you do when something's insulated,
Blech.
right? You cover it up. And here are a couple
the
of
brain
images
bussy.
of the insula. So here, what you're looking at is someone's opening up that sylvian fissure or that lateral sulcus and looking at cortical tissue. And here you can see a region of the cortex has been removed, and that allows us to see this cortical region that's insulated, that's the insula. So the insula does have a map of the body, but stimulation of the insula seems to provoke nociception in general areas, like an entire limb, like an upper limb or a lower limb. The insula is also associated with the emotional aspects of pain, and I'll show that, some of that to you as well. So whether sort of that unpleasantness, right? And the anterior cingulate is also associated with the emotional aspects, sort of that suffering or that unpleasantness of pain. And the anterior cingulate is this region in through here. So what are we looking at here? So we were looking at this upper image when we were looking at the primary somatosensory cortex, right? So now in yellow, I just put the central sulcus. So this was
I
the
don't know where the
primary
insula is, though.
somatosensory cortex. We looked at S2, and then we looked at the insula, which is buried in this sylvian fissure. So this is sort of this is a lateral view. Now we're
Where's the
looking at a
sylvian
medial
fissure?
view. What does this black structure represent? Does anyone know? So it's a myelinated bundle. Does that help? Big myelinated bundle.
They didn't indicate where the sylvian fissure is. I don't know where that
Word.
is.
Corpus. The corpus callosum. It's the corpus callosum. So the cingulate gyrus is all of this cortical area that surrounds the corpus callosum, but the anterior cingulate is just the portion that's in orange there. So that's the anterior cingulate cortex. So at any rate, that just gives you a visual of where these various cortical regions are located. Okay, so what have we done? We have talked about the spinothalamic tracts. And this
What
is an
have I
image
done?
from your textbook. I think it's a really nice summary image of the spinothalamic tracts. And you can see I've sort of separated out the neo and the paleo-spinothalamic
Oh, you know what it
tracts.
is?
The
Recently there was
neo-spinothalamic
a...
tract associated with those A delta fibers.
You know what I was... Recently I had a friend tell me
and
also
S1.
that new followers can't message within the first 24 hours of following. And I don't know why that's a thing. I gotta fix that. I think it's one of the security things that changed up on the channel. Let me fix that real quick. Oh god, I don't want to hear myself. I'm sorry, let me adjust that for you. I'm sorry if you wanted to chat. I think it was a new moderation thing. Channel privileges. It's one of the safety things too. Followers only mode. I don't know why it was on followers only. There you go. No wonder. No wonder. Anywho, there you go. I turned off, for some reason followers only mode was on. I had no idea. But there you go. No need to apologize. Thanks for what's it called? Letting me know. I would have never known. Because I'm a scuffed streamer and I forget some things are on. Or at least like some things accidentally get turned on and it gets under my nose. So I would have never known unless you had told me. No worries, no worries.
And then the paleospinal tract associated with the C fibers, the ILN, and then these 3 cortical areas. But the nice thing I think about these images is
it's
that
Twitch's
you
fault.
can see the cross sections
Blame Twitch.
as well as like get a sense of how these fibers are coursing from caudal to rostral or from inferior to superior. So we'll just do a quick summary. We have primary afferent fibers, right? These are entering the dorsal horn of the spinal cord. We can see the cell bodies in the dorsal root ganglion. Then we talked about the second order neurons. We talked in some bit of detail about the difference in the location of the second order neurons, but we know that the second order neurons, whether it's in the neo or paleospinal thalamic tracts, they cross midline. And I'll just mention here, you can see that there's a very specific organization of the fibers. There are a couple of times where I do ask you to memorize the specific organization. This is not one of them, but as many of the images, you'll get a sense, well, there's an organization. These aren't just all mixed together. There's a very clear organization of the central nervous system. But at any rate, what we see here is that the axons of the second order neurons, now we can see how they're traveling, right, anterior lateral aspect of the spinal cord, anterior lateral
By the way, the
aspect
Sylvian fissure
of
is the
the
long
brainstem.
diagonal line on the sides of the brain hemispheres. It separates the lobes.
Tegmentum.
Yeah. Thank you. I appreciate it.
And
I
then
do.
up to the
I
thalamus.
know
So again,
where
up
it
to the
is,
thalamus, and then
but
up
then
to the
like
various
in the
cortical areas
notes,
that we talked about.
she wouldn't
and
indicate.
This is the insula.
Sorry, my professor wouldn't indicate where the insula is on what I would want from the Broadsman area as like something that I would imagine that would be on the exam. Like if I see where to indicate where the insula is, I don't see it on the Broadsman, or she didn't give a Broadsman location on it. So I'm like, where is it? But it's okay. I have an idea of it.
Let me just show you. You can see here what's being represented. This region here is the insula. See how this cortical region is insulated, right? It's sort of covered over. So that these little axons here are representing fibers going to the insula.
Oh, well, that's useful.
Okay.
How relevant.
The last thing that I want to point out on this particular slide is that we can see that there are fibers that are passing to various regions. These are collateral branches, okay? So we're going to come back to those, but what we can see is that not all of the axons just go directly up to the thalamus. Some of them have these collateral branches that can
I'm
pass to other
definitely
regions.
gonna need to eat after this. I am so hungry, y'all. Ba-ba-bow. I think we're almost done with it. It's just clinical.
All right.
No, wait.
So
I
I
don't
think
know.
this
Maybe. We're
is
almost
a
done.
good
We're almost
time
done.
for, let's do just kind of a mental break.
Oopsies, I might have gone too fast.
First, well, actually, let's look at how you did, and then we'll.
Yeah, insula is kind of hidden. You can sort of see it in the cross section or by pushing the fissures around the tissues of the Sylvian fissure. I hope that's all she wants
Yes,
with the
excellent.
exam.
Okay.
I hope that's sort of.
So
I hope that's
a
sort of
couple,
what
I
it
mean,
is.
I could have asked a few questions here, like what kind of
A
section
parsing.
is
Can I
this?
ask? Are you a
So,
doctor
although I don't
or
think I
do you
would
go to
ask
med
that
school?
quite yet, but it's a horizontal or a transverse section, right? So it does, when you go back, when we look at some of the coronal sections, it's a horizontal or transverse section, which makes this the anterior limb, the bend is the genu, and where the
You're a
arrow is, that's
pathologist.
the
Wow,
posterior
that's
limb.
crazy.
So that's
That's
the
awesome.
posterior limb of the internal
This is
canal.
this is anatomical sciences in context of dental school. So, that's why I'm taking this
Okay,
class.
so I do have a couple of clinical correlation slides, just thinking
in
about content that we've talked about.
Dental school.
And it's possible that you'll have a patient
Makes it hard
with
to be a
something like
VTuber, I'll
this.
tell you
So I
that
just
much.
bring it up, and it also, I think the cases that I'm going to bring up.
Students are not
This
responsible
is
for
an
this slide.
anterior cingulotomy,
Then I don't want it. Honestly,
but
I honestly don't want
now
it.
we have, again, it's the
It's
part
too
of the
much
brain.
additional information. Skip.
It turned out like she'd have like patients with chronic pain. So
This is too much
So those are
additional
a few
slides.
kind
We're
of
done.
aside. Interesting things, but also I think really important as future dentists when you're working with patients with pain. I mean, why do a lot of people go to the dentist? Because something hurts. Okay, the last thing related to some of the clinical content is I just wanted to bring up what used to be called thalamic pain syndrome. It's now called central post-stroke pain.
I
So
thought
what
this
is
isn't
this?
relevant to our exam.
Okay. So again, I'm not going to ask you a specific question, but if you see a patient, with this type of pain syndrome, and also that what I have said is that it's when we get to the cortex that we're able to identify the nature and the location of a sensory stimulus. So then you might think, well, if their patient has a lesion to the thalamus, well, then they must not be able to perceive pain. But in some patients, they actually have severe pain. And so it's thought that it's because there's an imbalance in thalamic activity. So we have like the ILN, we have the VPL, and so when you damage one part of the thalamus, again, we don't really know why, but there appears to be some imbalance associated with these thalamic lesions that in some patients, they have severe pain. Right, so again, it might be what you wouldn't, that's not what
Since
I would
most
have
of
expected. I think
your,
you wipe
or
out the
since part of your
thalamus, and so
work
the person
lies
never gets
with
to the cortex and you never hear
neurophysiology,
it.
you
So just to
know,
be aware of that.
brain anatomy pretty
Again,
good.
if you're, maybe you bump into
I
someone that has
am
it.
so thankful that you found my stream because
Oh my
this is
gosh, it's time to go.
the subject of my exam. I have an exam on Tuesday on neuroanatomy and stuff like that. So that's gonna be a majority of what I'm learning. I think what we're going through. Let me see what we do. We've gone through a general introduction of the central nervous system, and then we touched upon autonomic nervous system and pain for today's stream. And then I got touch and proprioception. descending motor pathways, and then we touch upon cranial nerves. And then we have, I'm not sure if we actually touch upon central nervous system vasculature, but we might. So I'm not sure where we stop, but I think there's a little bit more. But yeah, cranial nerves for sure is one section. Hopefully you'll get through it successfully. I hope so too. Yeah, like even though it's Thursday and in hindsight you're like, man, like four days, wait, I can't do math. 96 hours. That's plenty of time. It's not plenty of time. I've always realized when it comes to dental school, it is never enough time. But it's sort of why I've now started to do the thing now where I have dictate between, or like I have balance between, do I stream studying or do I study off stream? And sometimes it works for me if I study off stream because I'm more focused in, and then sometimes I think it's really good for me to like actually like hone in and actually like sit down and study and force myself to study, because when I'm on stream I'm sort of held accountable, and it's nice because I can't goof off, because off stream I will end up like inevitably goofing off if I spend like 30 minutes watching a lecture and then I get bored or hungry and then I walk away. But I think when I'm on stream, like I can't really do that without looking like an AWOD. So that's sort of what's nice about these streams. So I'm gonna try to watch the majority of these streams, but I have a simulation lab in 2 hours, so I will be actually ending after this video, which I think ends like right now. I think this is the last slide I have to go through, and then I'm gonna make myself some lunch and then get ready for the rest of it. And then I think yeah, I think it's more streaming this later tonight, so it's good though. It's been nice studying with people, and then I'm actually like really thankful that you came by. Like it's nice seeing people from other aspects of the medical world come by. And it's also like nice because they're helping me. I really do appreciate it. Like I really do appreciate it. Some of this stuff seriously flies over my head, but I'm slowly and surely getting it. So yeah, it's been awesome. Thanks for stopping by. I really do appreciate it. But yeah, let's finish this up and then we can end our stream.
All right.
Oh, never mind. I guess I just didn't even want to talk about it. Alright, let's just look at the slide itself. Referred pain. Visceral and afferent fibers respond to excessive pressures. Excessive tension and inflammation in the visceral organs. And then these afferents will enter the spinal cord and be interpreted as pain in the cerebral cortex. So like if you have a heart attack. Visceral afferents from the heart enter the upper thoracic spinal cord segments, which converge on the same spinal thalamic tract cells reached by somatic pain fibers. The brain interprets the activation of these as pain in the somatic region. So like the left arm and the chest. I should probably highlight that. Which makes sense, or that's always what I've heard is yeah. That's always what I've heard, is that if you have pain in your left arm, it's because you might low-key have a heart attack. Thank you for streaming. Thank you for stopping by. It's been appreciated. I hope you enjoyed a little bit of me going through all this. I know it's not for everyone, and I know not many people will want to watch this stream, but I don't mind. I think it's just good for me, and that's what matters. So the pain from the heart is commonly referred to the pain on the right side of the chest, the left side of the chest and part of the left arm, since these areas send afferents areas send afferent to the same spinal cord segments. This is my hardest class in dental school, and for some reason, everyone else is actually like really good at it, which is really tragic. But this is easily my hardest class, which is why I have to study extra hard for this one. It just doesn't come to me as well. But I think this section is nice because it's more conceptual based than it is memorization based. Because because some classes are based on just memory, and I think you know this, right? Like going through like uni and stuff like that. Some classes are just based on pure memory, and then some classes are actually based on like sort of understanding the core concept. And anatomy is more times than not just memory, and I'm really bad at memory, or at least like I just don't have enough time to put in the hours to make flashcards and memorize flashcards. So yeah, like it's been tricky. But anyways, yeah. Hopefully neuroscience is better for me, because like it seems like it's more it feels like it's more concept based. Like it feels like I'm just going through physiology, which is the core conceptual class of my year. So I'm sort of enjoying it that much. I really hope that's the case. Anyways, I think that's about it for me. I'm gonna go ahead and sign off for now. And then what's my plan? Let me check my own schedule. I actually don't know what my own schedule is for today. Oh my god. My laboratory thing lasts until potentially 4 to 5. Usually 4. It's never as long as 5. And then I think what I'm gonna do is I'm gonna probably enforce a nap around that time. So then whatever time I do wake up between 8 to 9 Eastern, I think I'll return back and watch 1 or 2 more lectures. I think that's my game plan for today. Yeah, anyways. Thanks for the stream, Kyo Sensei. Thanks for stopping by. Thanks for hanging out with me this whole time. I know it's not the most fascinating streams in the VTuber world and stuff like that, but I hope I bring in a different niche, you know? Like, I hope you enjoyed it, because, you know, it's not riveting gameplay, but it is interesting. And you get to learn a little bit more about medical information if you're into sciences and all that. And you know what? Luckily, neurological anatomy is it's relatively interesting, I would say, compared to some other subjects. Some other subjects, it's like it's too mush, you know, like your brain just fries after a while. So it's nice. And if you have any questions, hopefully me and chat are able to combine our brain cells and like figure it out and stuff like that. So it's nice. We're learning together. It's not a gameplay, it's the guide to the game of life, you know. It's the game of life. It's not a race. It's not a race, y'all. It's not, we don't have to speed run life, even though it feels like my body is trying to. Okay, I really do appreciate y'all, but I'm gonna go ahead and take the 2 hours I do have left to go ahead and wind down and get ready before I have to do this all again and stuff like that. So I will talk to you guys later. Thank you guys so much. Kyotsukari for the good work. Kyoyasumi for the rest of the night. I'll see you later. See you later, everyone. Thanks for stopping by. Bye-bye.